Sorry, I think I am not audible earlier. Only I unmute. Yeah, good evening to all the participants. Welcome to day 6 on computer aided drug and vaccine design. So today we'll be discussing on molecular modeling, that is the small molecule modeling. If you remember, recall, we already discussed how to model the macromolecules, that is how to model the targets. Now we'll be discussing on how to model the ligand molecules. Okay, this covers in chapter 6. Now, before going to the session 6, can we recap the last session contents as usual? So, what did we discuss in the session 5? So, what exactly did we discuss in the session 5? So, come with the answers. Very good. I got answer from again Saraswati madam that we have discussed on network pharmacology, system pharmacology. That is actually, if you see in system pharmacology, network pharmacology is one of the branch of study. Okay, so where in system pharmacology, majorly you study on multiple targets, multiple drugs, and how these multiple drugs interacts with the multiple targets. Okay, so generally, if you study these interaction in the form of networks, we call that as network pharmacology, and of course, we have mentioned that is a branch of study. And the major purpose of studying this network pharmacology or system pharmacology is to reach the personalized medicine, that is, to reach the precision medicine for each and every patient. So the diseases like cancer can't be cured with the already existing drugs available in market. So we have to customize the drugs. The customizing the drugs, we also call it as tailoring the drugs based on the needs of the patient, based on the genes of the patient. Okay, so this can be achieved by having a knowledge on network pharmacology or system pharmacology. And then we have discussed on networks. Okay, so for protein networks, we discussed on string TB, and for the ligand protein interactions, we have discussed on stitch TB. Okay, so other than that, we also discussed on DC gene networks, that is the GNet, and we have seen about a network visualizer called Cytoscape. So for downloading the Cytoscape, one can go to the cytoscape.org. It's a small file you can download and install. So the purpose of this Cytoscape is that you can visualize almost all the types of networks. Okay, this is an universal kind of network visualizer used all around the world to visualize the networks. And we have discussed on databases like Indian medicinal databases like Impact and Chinese medicine databases like Herb 2.0. Not only we discussed about discussed that we have the drug molecules there, we also discussed how the disease interactions, okay, play an important role with respect to a specific gene. Like this we have discussed, isn't it? So we also seen the networks in Impact and as well as the Hub 2.0. Other than that, we also discussed something called metabo-analyzed. Okay, and we also seen network analyzed R. You remember? So these are the other things we have discussed. Especially I mentioned you in network analyzed R, other than visualizing the gene interaction networks and enriching the genes, okay, we can also able to use R programming for customization or filtration of genes, the top upregulated and downregulated genes. So this I also explained you through a case study. Like I've published two papers, research papers, one on ovarian cancer, the other on kidney cancer. Both these papers are related to network pharmacology. So I also I've uploaded these papers on yesterday to your WhatsApp group. If you go through my video contents, the recorded video contents, and if you see the journal papers, you can have an idea on how to proceed with network pharmacology. Of course, it's a largest chapter, but I concised and I provided you in brief like how to use the softwares and how to use the databases. Now, let me come across session 6. The session 6, as I mentioned, will be discussing on molecular modeling, there's methods and types. Participants, nowadays, so I found the interaction is decreased on today's session. I don't know the reason. So you ensure that you can go through the video contents regularly and do some homework, exercise, whatever I provide you. Okay, now let me take you to the molecular modeling. As earlier mentioned, we'll be discussing on modeling of small molecules. How to go for modeling of small molecules. So, what is molecular modeling first of all? So, molecular modeling it encompasses all methods, theoretical as well as computational, used to model or mimic the behavior of molecules. Okay, so if you see a molecule, what is a molecule? Molecule is a combination of atoms, isn't it? So the many atoms can combine to form a single molecule. So, if you see this molecular modeling, basically we use the molecular mechanics approach. If you see the mechanics, okay, molecular mechanics, the molecular mechanics generally we see in the form of dynamic motion, isn't it? So defaultly in molecular mechanics you have two types. The molecular mechanics are of two types. One is molecular statics, molecular statics, and the other is the molecular dynamics. But generally we observe all the molecules have the motion, isn't it? So if you see, if you want to determine the atoms, functional groups, generally we go with FTIR, you know, Fourier transform infrared spectroscopy. Here, we can distinguish the each and every atoms in a molecule. Okay, the functional groups can be identified. So especially the functional groups in a drug molecule. Okay, so if this is the experiment we use to identify the functional groups, okay, so generally this FTR uses a principle like the functional groups are determined using Brownian motion, okay, only through the vibrations. Only through the vibrations we can able to determine the atoms in the molecule. Okay, so if so, so default in molecular mechanics, we are studying the molecular dynamics, isn't it? Each and every molecule has a motion. Then what is that? Okay, so what kind of, even if you see this molecular dynamics, we can further classify it into three types of subjects. So more about that, we will be discussing in the subsequent slides. Molecular mechanics uses classical mechanics. So I was mentioning you, the molecular mechanics can be broadly classified into three types. The first type is the classical mechanics. You know, in classical mechanics, we study the Newton's law of motion. That is, F equals mass into acceleration. So we can also call this as Newtonian mechanics. Classical mechanics also called as Newtonian mechanics. So this is the first branch of molecular mechanics. The second is statistical mechanics. The molecular mechanics can also be measured through statistical mechanics. If you see a macromolecule like a protein, for example, if your protein is 200 amino acid, you know, amino acid is a molecule which is made up of several atoms, isn't it? CHON. So we find several atoms in a single amino acid molecule. And if you see a 200 amino acid protein, you have that much number of atoms, 200 into an average of, if you have 12 atoms, 200 into 12. Actually, each and every amino acid has an unique atoms. So you have approximately 200 into 12 or 200 into 15 atoms. So each and every atom, in a system has a kind of a Brownian kind of motion. Okay, so a random motion you can observe. And all these motions can be measured in the form of energy trajectories. This can be measured in the form of energy trajectories. Okay, each and every atom. If you have 200 into 12 or 13, how many atoms you have, this much energy trajectories you can able to find. So whatever number you found, okay, this much number of energy trajectories, okay, we sum up to get a single energy finally. So for a protein, you have one energy. Then you go with the energy minimization to check the stability of a protein. So the protein has attained the folded state, and whatever you have calculated in energy minimization, that is the best energy for the folded protein state. Okay, so what I mean is, so you have 2600 energy data. For this, we try to use the statistics for multiple data. Then if you use this kind of statistics, and if you study about the mechanics, then we call this as statistical mechanics. The third branch of study is the quantum mechanics. Quantum mechanics. Okay, here in quantum mechanics, each and every atom is measured by passing light. Quantum, the name itself implies we generally measure the molecules based on the heating of photons. The light is nothing but a pack of photons, isn't it? If light hits the molecule, you can able to measure the molecule. Okay, so this is how we basically or broadly classify the molecular mechanics. Classical mechanics, again I'm telling you, it is a Newtonian mechanics where we study the Newton's law of motion, all the Newton's law of motion. And then if you see the statistical mechanics, we study multiple energies. Okay, we study the multiple atoms energies, and we study in the form of a single macromolecular energy. So we do energy minimization protocol before going for docking or simulation. So this is done only through this statistical mechanics. And in quantum mechanics, we use Schrödinger equation. Actually, a particle, okay, in the matter is not moving just like this. If you have a particle like this, if you push, it won't move like this. It is not going to form a kind of a linear thing. But according to the quantum mechanics, if photon is going to hit, the photon is going to hit the particle can move in the form of a wave-like patterns. Okay, so this kind of wave-like patterns can be measured through the Schrödinger wave equation. Okay, so this is something about molecular mechanics, which we can observe in docking as well as simulation. These are some of the methods of computer-aided drug and vaccine design. And if you see the molecular mechanics, we use the Born Oppenheimer, actually Born, BON, I believe. Born Oppenheimer approximation is used where you calculate the potential energy of all the systems. So whatever atoms you have, you calculate everything for all the atoms and you calculate a single energy. Okay. So generally, it's a combination of different energies. We'll be discussing more about the Born approximation model in the subsequent slides. If you see the atomistic molecular mechanics, okay, each atom is simulated as one particle. This is an assumption. This is an assumption we will be making before starting the molecular mechanics. You remember, if I want to open and show you the 3D structure of a protein molecule, I suggested you to install Discovery Studio visualizing. How to visualize the 3D structure of a chemical compound, a drug. So tell me the visualizer name for which we can able to visualize the drug or chemical compound. I just asked you a question, participant. Just interact with me. What is the software we can use to open the 3D structure of a drug, chemical molecule, or even a DNA, RNA, whatever ligands we have discussed? What is the visualizer we use? Give me some examples. The best visualizer I mentioned you is again very good. The BioVia is the name of the company. In BioVia, we have Discovery Studio Visualizer, the TS Visualizer. Okay. So do you, I think you have forgot everything. Yesterday, day before yesterday, also I have taken you to this example. I have downloaded the chemical compound from the NCP PubChem, and I believe I have showed you how to open it. See, if you want to open a chemical compound, this is the chemical compound 2D structure. I showed you using Discovery Studio, isn't it? And I also have downloaded a 3D structure, and I showed you in the Discovery Studio. The 2D structure is going to have a single plane view. This is a single plane view. Okay, so you can't able to find in X, Y, Z directions. If only if you download the 3D structure, because you have both 2D and 3D structures in NCBI PubChem. Sometimes for molecules you may have 2D, but you may not have 3D. Okay, but for docking and simulation, it is must to download only 3D structure. Only this is eligible for docking and simulation. You can't use this structure for docking and simulation. This is just for taking a note. You can put in PPT, you can put in thesis, no problem. But you can't able to do for any computer-aided drug design studies. So better to use only this kind of a 3D structure. You remember what is this? What is the name of this molecule? Acetyl salicylic acid. It is aspirin. This is the structure of aspirin. Got it? Okay, now let me take you further on the PPT. So I was explaining you that the each atom, okay, in that even whatever chemical compound I have shown, is simulated as one particle. Each particle is assigned a radius, typically the van der Waals radius. Generally here, in these softwares, in the visualizers, we use a radius of 1 angstrom. We use the radius of 1 angstrom. For one atom to the next atom, you have 1 atom radius. And each and every atom, this is one atom. This is another atom. Whatever I select, you can see that yellow color. This yellow color is one atom and this is another atom. The red color in all the visualizers, not only in Discovery Studio visualizer, if you see in Rasmol, Swiss PDB viewer, all these visualizers, whatever visualizers you find the oxygen is in red color. Oxygen, the universal color in the visualizer for oxygen is red color. And the universal color for hydrogen is white. And for carbon is gray color. So you can check it in any visualizers, you get these kind of colors. So even this is universally adopted in developing this kind of visualizers. So one can able to remember that this also have is assigned a radius, typically a van der Waals radius. You can find the polarizability and a constant net charge. Okay, generally these are derived from quantum calculations. You know, These molecular mechanics, we generally study the interactions in the form of bonded interactions and non-bonded interactions. The sum of bonded interactions and non-bonded interactions is what? Total interactions of a molecule. So if you see this, we'll be seeing, I think we have an animation, it takes some time. bonded interactions generally are treated as prints. How it is treated? So actually, yeah, we have to wait. No, I mean audible participants to you. Yes, yes or no? Yes,
Yes,
part.
sir.
Ah, yeah, yeah. Okay, thank you. So we have some animations in this PPT. So it's taking some time to get loaded. The bonded interactions are generally treated as prints. Okay, so you can able to find a spring-like motion when you connect one atom with another atom. Okay, then what is the weight of an atom? First atom, and what is the weight of second atom? This can determine the kind of bond energy. So bonded interactions are classified into bond stretch, bond torsion, and bond length. Okay, now let me go to this slide. So we can also able to go with simulations by studying the molecular mechanics. Okay, so I told you earlier that in molecular mechanics, the first mechanics what we study is the classical mechanics, where we use the Newtonian law of motion, and then we go with the statistical mechanics. So in the statistical mechanics, these atom contacts can be studied. This is first bonded interaction. Okay, there are three bonded interactions. The three bonded interactions, the first bonded interaction is the bond stretch. So you can able to see. So this is the initial position, but it is stretching up to this part. Okay, so you can able to see this bond is going to stretch, and the potential energy of the bonding energy bond stretch can be calculated using this formula, where P naught is the initial length, okay, and B is the stretched length. So this is up to this is B naught, but up to this is small b. Okay, so we will be calculating the bond stretch energy like this, where Kb stands for force constant. If that is first bonded interaction, the second bonded interaction is the bond bend. So the atoms bonds can also bend like this. For this, whatever small angle you have is the theta naught. Whatever is the wide angle you have, that is final angle theta. So summation of k theta into theta minus theta naught whole square gives you the bond bend. The third bonded interaction is the bond torsion. So in bond torsion, you can able to see this atom is rotating along the axis. If so, okay, we can able to calculate this bond torsion through k phi 1 plus cos n tau. N tau is how much this is actually moment of inertia minus the pi, the angle. Okay, so this is something about how to calculate the bond torsion. So bonded interactions are nothing but to calculate the bonded energy, you have to sum up all these three bonded interactions. Okay, so these kind of bonded interactions you can able to observe in ligand. So especially if you try to use a flexible ligand, of course you can able to obviously observe this, and also you can observe with the receptor. So even in receptor, we have flexible type, isn't it? Nowadays, whatever uh, docking softwares we get, okay, these softwares have utilizing the flexible ligand versus flexible receptor dock. Only the old softwares we have rigid versus rigid, but nowadays we have all the flexible thing. So obviously we can anticipate these bonded interactions. Of course, this is also used to calculate initially the force. If you calculate the force to the force field, so force field into distance is what the energy. This is how energy is calculated for each and every atom. Then you sum up all the energies. And if you see the second kind of interactions are non-bonded interactions. So non-bonded interactions are of two types. Number one is the van der Waal. Number two is the electrostatic. Okay. So van der Waals and van der Waals, and the number two is electrostatic. For van der Waals, energy can be calculated through this formula, whereas A and C stands for the van der Waals constants. K is the radius. Okay, and electrostatic, of course, this comes under Coulomb's law of attraction. If electrostatic is a force of attraction, van der Waals is a force of repulsion. So van der Waals energy can be calculated using this formula, and electrostatic uh, we can able to calculate through Qi Qk divided by Drik. Now let me take you to the next line. So if you have animations, it takes some time. Wait a minute. So we are discussing something about. So let me go to the. So today we'll be discussing on how to use chem informatics software like ASD Chem Sketch for drawing the chemical molecules, and how to draw the peptides, how to construct the peptides. So we'll be discussing that also on today, and how to simulate the RNA. Okay, so this all we'll be discussing it on today. Okay, let me close the program. Yes, I was explaining you. I was just mentioning you that I'll be explaining you about how to use the ACD Chem Sketch. For ACD Chem Sketch, okay, I've already installed this freeware. So defaultly in Google type for ASD Chem Sketch. But there's a lot software, but there's a freeware. Anyone can download this. Okay. So to download this ASD Chem Sketch, one can go to the website ASD Chem Sketch. That's it. So the recent version is 12.0 free download. So go to this and you can download this. Okay. asdlabs.com. Okay, this is a freeware. See, this is the software. This is how you can able to find, and this is the homepage of the ACD Labs ChemSketch. Download ChemSketch freeware. It's available. But we can also install this whenever there is a need. Okay. Now, if I want to search a similar drugs, for example, if you see the aspirin, this is a pain reliever. This acetyl salicylic acid is a pain reliever. But unfortunately, earlier everyone used aspirin for relieving from body pain. But later it was identified, even though once upon a time it is a FDA approved drug. But later the patients were suffered from cardiac problems. So just because it is arising the cardiac problems, that is, it's giving some kind of a side effects. Okay, they are using an alternate drugs. If you want to find aspirin related structures, okay, you can able to check even from this ASD Chem Sketch. So see, first we can draw an aspirin molecule. So how the aspirin molecule looks like? So first I can show you, and then I can try to draw. Aspirin, you find C double bond O OH. Okay, this is actually OCOCH3. C double bond OCH. Okay, so that's what you can find the draw. Now I am going to draw this molecule. So I just drawn this by selecting this benzene ring, and for taking this alkyl group, I click here. I got this, click double bond. Okay, now I got like up to this. I just used click this and I made this up to this. Then if you want to click, before going to this, I want one more thing. So I click this. Okay, now if I want double bond over here, OH here, what I'm going to do, click this O. So you had double bond O. Now click here, OH. Got it? So benzene ring followed by COOH is designed now. The next is OCOCH3. So to draw this, now click C, because we have O. If you click anywhere, you get O. So we have to come outside from the O. So click C. After clicking C, default it is in the alkyl group. Now click here. You got like this, and you have double bond. Click here. Okay, you have double bond O. See here, here O. So here only you have double bond O. So again click here. No, this is not right. Do we have an eraser here? Eraser. We can check for an eraser at present. Somewhere an eraser is there. So this is actually delete. Whether we can delete a particular thing. Yes, I have deleted the particular thing. Now if I want to draw a structure, click here. Okay, because I want a structure like this, a double bond. So better click at the top. No. Okay, later I can delete this. Still I can use, no problem. So I click here. Now I got double bond O. So this CH3 is right, but only thing is that we should have O here. Here we should have O here. O, O. So for this, click O here. If you click here, O you got. If you click here, got double bond O. This structure is established. Whatever structure we have for aspirin, we got this structure now in ASD Chem sketch. Okay, so whatever structure you got, okay, if you want to check what the structure I have drawn, so even you can check from this option called PubChem. If you search for PubChem, okay, so if you want to search exact structure, you can click this search exact structure. But I told you that I'm going to search related structures of PubChem. I mean related structures of aspirin, because aspirin has side effects. So I'm going to search for substructures. Now it's going to show results in the browser. If you want to see in the Chem sketch, you can see in the Chem sketch itself. But if I want to see the results in browser, default it is there. So now click OK. Now what is going to do here is, in ASD Chem sketch, whatever molecule we have drawn, the related substructure, okay, is going to search in the existing browser. And similarly, so it takes some time. No error. You may try a more specific request. Okay, once again, I try with the E molecules whether it's working or not. Search substructure. Yeah, now it's taking you to the E molecules database. Like PubChem, we also have E molecules database. See, these are the substructures. We have substructures like this. To know about the compound name, you can click here further and you can export that. So many substructures of aspirin we have retrieved. This can also have the painkiller activity. Only thing is that you have to check the activity through molecular docking and MD simulation for stability with particular target receptor. Whatever target receptor you use for aspirin, especially you use COX2. So the same COX2 can also be used here. Okay. Okay. Now we got the result for the E molecules. Similarly, if you want to search the substructure from Spider, click here. It can take you to the output. Okay, but now if you want to get the smiles annotation, whatever structure I have drawn is a 2D structure or 3D structure. This is my next question. The structure, what I've drawn in ASD Chem sketch, is 1D structure or 2D structure or 3D structure. Kindly unmute and answer. What structure is this? I told you it is a structure of aspirin. But what kind of a structure? 1D, 2D or 3D? Yeah, participants, come with your answers. I'm asking so difficult question to you. Am I audible to you or not? 1D is right. Very good. Bhargav, Saraswati Madam. So everyone are answering well. So no 1D. You answered 1D, isn't it? The answer is 2D. This is a 2D structure. Then what is 1D structure? 1D structure is this. See this miles notation. If I click this miles notation, you got this. So this is what, sorry, this is what we call it as 1D structure. So whatever is the one OC double bond O, okay. So this is actually a 2D structure. A 3D structure is what I showed here. So this is a 3D structure. So a 2D structure looks like this. In the visualizer, it looks like this. In ASD ChemSketch, it looks like this. That's it. That's the only difference. But it can also convert this by clicking a 3D optimization. So this is how a 3D structure looks like now. Okay, a 3D structure looks like this. Can I remove the smiles? No. If you want to delete, click this, delete. I can use an eraser. Yes, that is removed. So eraser you have, to erase it you can use this. Okay, so like this, if you want to get a 3D, you can click this 3D option. So one thing you have to remember that this software tool is used not only for creating the 2D, also 3D structures can be created. And you can create all the molecules, say like even the rare metals. So for rare metals, you can use whatever symbol you use. Okay, everything we can able to create it. We have table also. We have table. Yeah, see this table. So we can also, if you want to create the functional groups, you can click this so that you can create it instantly. Instead of drawing or O, S double bond O, double bond OH, if you click simply and if you select somewhere, it will be joined in that backbone. Got it. Also, we can able to find the structures of the amino acids. If you link the amino acids to form a peptide, still you can use this software. Okay, so you can have the functional groups as well as you have the amino acids, which can be linked easily in this chem informatics software. Not only that, we can also calculate the properties of the chemical compound whatever we have drawn. If I click this, okay, log partition coefficient. So whatever molecule we have drawn, for that you got the partition coefficient values. That is 1.19 plus or minus 0.23. So 1.19 is the log partition coefficient. Like this, we can estimate few other properties. Okay, physical-chemical properties. We can see, we can able to calculate the aromaticity, we can calculate the tautomeric forms, we can add the hydrogens. So we have plenty of options in the ASD Chem sketch. Okay, like this, ASD Chem sketch. Now we'll be seeing another tool. So that is even the Discovery Studio can be used. File new molecule window. So now I created a new molecule window. So we can see a black screen. Okay, here if I want to build a peptide, okay, build a peptide. Okay, for example, like whatever peptide I mentioned you on yesterday, I told you in IGM project, We have last three atoms as tryptophan, and we have to construct six amino acids randomly, isn't it? But you have thousands of combinations. So, for example, if I create this kind of a combination, first arginine, and then I am linking with methionine, I'm linking with tyrosine, and then valine. So already we have whatever I have drawn. Okay, you can able to find somewhere here amino acid chain and amino acid. Yeah, so you can see up to four amino acids I have linked. Now proline, so five amino acids came, and isoleucine, some six amino acids came. Now if I want tryptophan in the tail region, okay, so this is how a peptide looks like. The nine amino acid peptide can look like this. So whatever molecule I have drawn, okay, so this is the thing, okay, you can able to find the molecule, you can find something else. No, only the amino acid you can able to find here. Okay, so you can see this in the bottom, what amino acids I have created, I have used to create this kind of a peptide. So whatever peptide I have created, okay, now click file, save as. Now you can save like .pdb, or you can save like .mol or sd. Okay, pdb is here, and even you can save these kind of files, smiles format, and other formats are also available here. Okay, so to construct a peptide, you can also use Discovery Studio Visualizer. Okay, you can also able to save it. And similarly, to build and edit nucleic acid, we also have tools. Nucleic acid, that is DNA, RNA. Okay, we have these kind of tools available in Discovery Studio Visualizer. For this, there is no need of any license. The freeware support you to construct these kind of molecules. Got it? So now we can see one more kind of, if you want to, if you are not getting a result when you talk a peptide with a protein, and if you have any doubts related to the peptide structure, whatever you obtain, correct or not, I suggest you to go with, okay, instead of going with the Discovery Studio Visualizer, a reliable method what you can try is pepfold 3. This is also one of the methods where you can use an online freeware to construct the peptide. So in Google, I defaultly search for pepfold 3. It directed me to biosurf.rpbs .uni. So in Google, defaultly the first link will direct you to the pepfold 3 homepage. Now in the pepfold 3, click run pepfold 3. Okay. So after this, whatever amino acid you want to create a peptide, I have already created a peptide with this, isn't it? Arginine, methionine, tyrosine. Arginine is given by R, methionine M, tyrosine Y. So give a single letter word for each and every amino acid. Now, what is the 456? Valine, proline, isoleucine. Valine, proline, isoleucine. Okay, valine, proline, isoleucine. So six amino acids I have typed. The obviously the 789 is tryptophan, isn't it? So tryptophan, three tryptophan I have typed. So this is a 9 amino acid peptide. So to construct this peptide, just go down, click run. So it's asking for a captcha. So it's going to load you with, so even without signing in as a guest, I can get the 3D structure of a peptide. Simply download the peptide, whatever you get in 3D structure. So the job is running. It takes some time to generate a peptide. After it generates, you can use it. Okay. Okay. Now let me take you to the PPT where I left. Let us see. So we have just discussed on how to draw the chemical compounds and how to draw the peptides and even how to draw the DNA and RNA molecules using DS visualizer. Okay, and majorly I want to mention you is that in molecular modeling, we basically study about molecular mechanics. Default it is a molecular dynamics. In molecular dynamics, we will be discussing on classical mechanics, statistical mechanics, and quantum mechanics. So, if you, for example, if you want to estimate the molecular weight of a protein, or if you want to measure the weight of a protein, obviously what we do, we use spectrophotometer to measure the absorbance. So spectrophotometer, what it uses, obviously it uses light. If you want to measure the functional groups present, the functional groups are measured, or I mean can be identified only through infrared. So obviously infrared again you are using a kind of a light, isn't it? So you are using not a visible light, but you are using a infrared light to measure the functional groups. So obviously one can able to infer that if you want to measure any properties of a molecule, we have to use the light source. And of course, it can be UV light or infrared or a visible light. Okay, so obviously where we are using a quantum mechanics and Schrodinger wave equation applies to estimate all this. Okay, yeah, the PPT. Yeah, actually, if you see this PPT, I've already explained you how to model the protein using Swiss modeler and how to validate the protein using Townsend plot and how to go with ITSR, how to go with PEPFOLD 3, and how to design the structures of chemical molecule using ACD Chem sketch. So this is what you can able to find in molecular mechanics. Okay, so we have completed the chapter of molecular mechanics on today. Anything left out, I mean, anything you don't understand in the previous sessions, you ask me, I can take you once more. So I have completed today's session on molecular mechanics. If you have any doubts in the previous session, I can take you further. So we have some tools if you can able to spare because we have sufficient time, isn't it? So I can teach you something about some tools like you see Swiss ADME. So if you see this Swiss ADME, if you default it as Swiss ADME, you can able to see not only that ADME is available in this website, we have Swiss target prediction. So in Swiss target prediction, okay, so like we already discussed in the previous chapters, but I didn't show you the target prediction, okay, because I just kept hold like only after teaching the molecular mechanics I can go ahead because see here you have a Marvin Java script sketch, okay, so where you have to draw the molecule, okay, this is designed by Chemaxon. Either you have to draw the molecule or you have to paste the smiles format. So if you do that, we can able to predict the targets for the specific compound. Okay, so either draw the molecule, whatever aspirin I have drawn, we can draw the molecule, a simple molecule I can make it, or else if you want to make the job simpler because this is very known compound, we can go with the NCP PubChem. I think we also have a smiles format here. Can we copy this? No, don't. I have to do the eraser. Smile format, can I copy it? No, I'm not able to select it properly. So we have problem with it. So better I think you can go with the PubChem and copy the smiles format. Aspirin. So I'm going to take you to this compound and we are going to take the smiles format in the smiles format, I select this, and after selecting this, I paste it. Okay, now predict targets. So they got an aspirin immediately. Now you are checking what are the possible targets, okay, protein targets for aspirin. So if you don't know what exactly is the important target of aspirin, I told you it's a COX-2 receptor. Can we check whether we have a COX-2 or not? So other than this, so COX-2 cyclooxygenase 2, see here. So we have probability. So COX-1 and COX-2 has equal probabilities. Okay, so just because it's targeting COX-2, we are getting living from pain, body pain, no doubt in that. And similarly, you can see it is a dopamine transporter, but it's a less probability. So like this, you can see so many kind of target receptors for that compound. Okay, so one can able to search the targets, the important targets for a compound using this. So the layman can able to study the drug design even from this tool. Like, however, I am gone with Swiss target prediction. Okay, there is a tool called Swiss Bioisosteer. If you want to find the kind of stereo isomer for a compound, okay, for example, you can get a compound of a D-lactic acid. You type the D-lactic acid smiles format, and you just check for the possible kind of isomers. Can we check with the thing? First, we can try with the aspirate. Let us see what is going to happen. So generally, we go with the stereoisomers. We have a smiles format. Yes, we have. Let us check what we get. It's getting running. We are also getting this information. But we are getting. Oh, I've gone to the Swiss area. No, I was checking with bioisosterum isomer, isn't it? Here only I have to paste the smiles format. Now, email is an option. Query. Please highlight points with R. So anything you want to create a kind of an stereoisomer. For example, you want to have this OH query highlight points with R. So R is this actually. No, it's better to use the D-lactic acid. We can't get if you use this kind of thing. Okay, this is not a proper kind of thing. Better to use a kind of a stereoisomer, and you can check the Swiss uh, using this tool. You can check the stereoisomers, and similarly, we can check with Swiss similarity. Swiss similarity can tell you the we have to just upload the chemical compound structure, no doubt in that, and then we can check for drugs, bioactives, commercial or synthesizable. You can check any of this. Okay. So for example, if check for a drugs, okay, so you can able to see this information. That is drug bank CHEMBL. I can increase the font and show you. See, everything we can learn, even the ISO stereo ASMR, if you want to know how to use it, we have even with an example. Okay, so you click this in an example and you can check for the query. Okay, you get an answer for that. Anything you can learn. Okay, there is no doubt that you won't get any information. So first learn from the examples, then you try with your own kind of a molecules. For a simple molecule, I got this kind of information for the Swiss bio isostereoisomers. Okay, that is total polar surface area versus partition coefficient. So each and every dot is a drug. Okay, this much number of stereoisomers we can get for this kind of a structure. Got it? So like this, we can also download this information in comma separated value file. This is an Excel sheet. So whatever isomers we got, okay, bio stereo isomers, we can able to get the information. We can download it. We can get the smiles from it. We can work further on that. Okay. So how better it is, how similar it is, how worse it is. How about the physicochemical properties of the drugs? All this information we can able to get if you search through Swiss bio isostate. So now I was explaining something about Swiss similarity. Okay, that is if you check a particular, we can able to check a particular drug, and we can also check with the approved drugs. So you have approved drugs, bioactive drugs, commercial drugs, and accessible drugs. If you click for bioactives, you can find these are the databases available for that compound. I mean, available for that aspirin drug. And if you go with the commercial, these are the databases. You know, these are actually vendors. They can supply you that kind of a drug, whatever you want. Got it? So this much number of vendors are there. Okay, so like this, you can able to get the information, okay, of a drug, okay, or it can be a bioactive or commercial. So all this information you can get from Swiss Clarity. And similarly, can one can check with the Swiss side chains. So we can go through that kind of thing, and we can try with any kind of examples. Okay, so in Swiss side chain. So you can this is well known Swiss param. Swiss param is Swiss parameters. I think the net speed is not sufficient enough, or at present it's not working. If it works, you have to simply upload the drug, and you can get the physicochemical parameters in Swiss para. Okay, so this is something about the usage of tools. Okay, for finding for a particular drug. So you know, even the NCPub PubChem can also be used to search for similar kind of a drugs. So if I go going for aspirin, I'm getting an aspirin. So see, in aspirin you have similar structure search. If you want to search for it, if you click it, you will get the similar structures from here itself. And you can also get the medicinal, medical literatures in PubMed, MESHQ. Any questions? Anyone is going to ask the question? Okay, so I've just explained you on how to model the molecules and how to search for the relevant similar structures of the molecules, and how to predict the targets, other than how to use the Swiss ADME. We also discussed everything. And in this pro that what is that pepfold 3. So to download the 3D structure, okay, you have to scroll down. You have model1.pdb. You have to click here. Okay, so if you click here, you get these coordinates. So these coordinates you have to copy it, and you have to paste in notepad. You have to paste in notepad. So I'm going to create a file, new tab. So create the coordinates, and now I'm going to save the peptide. The peptide I'm going to save it here in CATVT. I'm going to save like peptide.pdb. Whatever I saved like peptide.pdb, we can able to visualize it. Okay, we can able to visualize it. Using the visualizers. Okay, so only thing is that you have to copy and paste the coordinates. Actually, these kind of a peptides, uh, we can use it for epitope based drug design. Okay, T cell epitope or T cell epitope based drug design. Okay, so we can also open in Swiss PDB where we have multiple visualizers available. If it is not opening in Discovery Studio Visualizer, we can open with some other kind of an apps like this PDB viewer, and we can see that. We open ways we can explore on more about how to use the PDB files, other that is peptide PDB files in vaccine design chapter. Okay, so that's it. I have completed basically on the molecular modeling of molecules. The final thing what I want to explain is if you want to simulate the RNA, there is a server called SimRNA server. So if you feed a RNA sequence, you get these kind of a sequence. I mean, you can get these kind of a structure. This is actually a kind of a tRNA structure. Okay, this is a tRNA structure. You can able to get from the SimRNA. But actually, generally, there is no need to use the tRNA structure for us. Okay, generally we go for the DNA, etc. But we don't find the application. But if you want to get this information, you can get from SimRNA. Okay, that's it. Any doubts you can ask me. I have completed today's session. Any doubts you have? If no doubts, so thank you very much for your interaction and patience. Okay, so on the next, on tomorrow, we'll be discussing on force fields and quantum mechanics. Okay, the force fields, energy minimization, all these things we'll be discussing on tomorrow.